Or yeah.
Like, oh. Because I literally was like looking up stuff because I'm like, I don't understand this. And then I was just like looking at the author and I was like, oh.
Yeah, I had another stats on to category of data, and it was like all the stuff we were learning was like how to use the package that the investor like,
Zoom too.
Yeah.
Okay.
It's fine.
Sorry.
No, it's okay. Change the linger.
We good to start or is it?
I'm gonna introduce you before you start.
Yeah.
Okay. Hello, everyone. Thank you for being here. Today, we are very happy to welcome Kyle Stahl. Kyle is an alumnus of our program from class of 2017. Yes. And then he went on to do a business analytics degree from the Carlson School. He has since been working at Cargill, where he is a data science supervisor. And he leads a team of data science specialists in working on problems in machine learning and optimization in the agriculture industry. And he also teaches a data science class in the IT infrastructure program in the College of Continuing Education. So we are very happy to have you.
Before we get started, I want to take an understanding of your guys' background. Who has heard of machine learning or taken a machine learning class before? How many people have built a machine learning model or trained a machine learning model? What packages or programs do you guys use or software tools? MATLAB, Python, or yeah. I was going to start out with an introduction to myself, but I already did it. Pretty good introduction. That was basically all I was going to say. A little bit more background on our team at Cargill. We're like a centralized consulting group for the rest of Cargill's businesses worldwide. So a lot of the problems that we solve are anything applied math to business. So demand forecasting, smart manufacturing, supply chain optimization, discrete event simulation. There's a lot of overlap between data science and industrial engineering. Today, what are we going to talk about? I think the best way to summarize this topic is what happens after you build a machine learning model. How do you get the results of that into the hands or into the minds of the people that need to use those results to make decisions? And the new-ish term for that is MLOps. And the main parts we're going to cover is how do you deploy a machine learning model? How do you monitor it after you deploy it? And what do you even do after that? How do you update it when things change and you need to train a new version? These are the problems that a lot of machine learning practitioners are struggling with throughout the industry. A lot of big tech firms have it figured out pretty well, but most companies are still trying to figure out how to do this in a way that works for them. I think it used to be maybe 5-10 years ago that building and training a machine learning algorithm was hard. But nowadays, there's so many different packages and software tools available that getting an accurate enough model to solve a problem is pretty easy. The hard part is how do you integrate that into a software in a way that people can get results from it regularly and integrate it into their work. And I also wanted to mention that there's a focus on machine learning models in this space because machine learning has been the hot topic for the last 5 or so years. Today it's LLMs, large language models. It's a different talk show. But almost everything when I reference a machine learning model also works for optimization models, LPs, mixed integer programs, and that sort of stuff. I think a good clickbait headline for this talk would be an introduction to software development for engineers and for scientists. So I'm going to start out defining what is MLOps, and the first part of that is what is machine learning. You know, a lot of people are familiar. We'll do a quick crash course. When I say machine learning, I'm referring to algorithms that teach a computer to learn relationships of data. They're often very complex algorithms applied to very large data sets, but it could be as simple as linear regression, 1 column, 2 variables, and 30 rows of data. The two main types of machine learning are supervised and unsupervised learning. With supervised learning, you're trying to predict a label variable or a target, usually denoted as Y, based off of a set of feature variables, usually denoted as X. From a statistics background, these would be dependent and independent variables. For some reason, the machine learning community decided to rename things that had perfectly good names to begin with. The other type of machine learning would be unsupervised. With unsupervised learning, you don't have anything that you're trying to predict. You're just looking for patterns that exist in the data set. So the one version of that would be clustering. You're trying to find data points that are grouped together in a certain way. Another version is association. The most common type of machine learning that is used to solve practices in a commercial setting or solve problems in a commercial setting is supervised learning. We're trying to predict something that will happen in the future or predict something that we don't have data about yet. And the two main types of supervised learning are classification and regression. With regression, that target, label, independent, dependent variable, whatever you want to call it, is numeric and continuous. With classification, we're trying to predict something that's categorical. Could be binary classification, a 1 or a 0, or you can do multi-class classification. I'm going to do a quick example that I'll reference later in this talk too. How many people are familiar with the Titanic data set? It's a popular introduction to machine learning data set with a website called Cargill. Cargill is a website that hosts machine learning competitions. So your goal here is to predict who is going to survive crash with the Titanic based off of these features. So it's a classification problem. And in this small example, we're going to try and predict who survived based off of age and gender. Because the theory is, or our hypothesis would be, women and children are let on the lifeboats first and more likely to survive. So we get our features in one data frame in Python. We get our label, our variable that we're trying to predict. Common practice to do train test split. So you'll split off and save part of your data set so that the model doesn't get trained on it. So you get a little out of sample accuracy to know how well it's doing. There's some common pre-processing steps that you need to do. This is taking that age column of our data and normalizing it to have a mean 0, standard deviation of 1. When we do a one-hot encoding of categorical feature, we can't do math on male or female. So this is going to convert that variable into 0 and 1. I don't know which one represents which. It doesn't necessarily matter to me. And then you define our classifier. The Python package scikit-learn has a bunch of different classifiers you can use. Logistic regression is probably the most common. This is a simple neural network. There's k-nearest neighbors, XGBoost, support vector machines, all fairly easy to implement. That's kind of the data that we have or what we're working with. We're taking age and gender, and we're trying to predict a 1 or a 0. And then we can use our model to make predictions about that set that we didn't use to train the model, our test set, and calculate our accuracy on our test set. And we can see the accuracy is about 74% of the people that we thought would survive the Titanic actually survived. And we end up saving that to a file. This pickle Python package is just a generic, take any piece of data, any Python variable that we have, and dump it into a binary file. We're going to use that later to read it back into another program and deploy this model in a way that other people could try and give predictions about the next Titanic. Hopefully there's not a next Titanic. Practice use case. Any questions so far? The next part of MLOps is DevOps. DevOps is a software engineering concept that was popularized in the late 2000s, and then it was a new way of thinking about building software. The old way, before the popularization of DevOps, software engineering was split into two different teams or two parts, the development and operations. And both had different goals and different priorities. Your development team was focused on adding features, fixing bugs, testing, writing documentation, in general, just trying to make the software better and pushing changes out, and made them a little bit more aggressive in doing so. The operations team was responsible for hosting the software, scaling it, security, fault tolerance, monitoring everything, and they would naturally be a little bit more risk adverse in doing so. And problems would be enhanced by having these as two separate teams. The idea behind DevOps would be to combine these teams, have them communicate more, and hopefully make things run smoother. And it seems like a simple concept now, but 15 years ago, it was kind of a revolutionary idea in the software industry. Improving that collaboration between the two teams led to all sorts of innovations. There's a lot more automation in testing and deployment after this. But the main thing was to have continual feedback into the development team from the operations side, that bugs could be identified and fixed faster, which led to smaller changes and faster release cycles and more stable software. So this is probably why a lot of apps on your phone want you to update them once a week or every other week, because most software teams are following these type of principles. MLOps is the emerging field that combines machine learning with DevOps, or I usually just say machine learning with software engineering. So why is this important? There's going to be relatively few examples of mathematical models, whether it's in a commercial setting, whether it's a machine learning model or an optimization model that doesn't get integrated into software. It could be a script that runs on a scheduled basis to save some results, or it could be running directly in a web app, a mobile application, or maybe it's hosted as a completely separate service that anyone else on the internet can use and get prediction results from. All of those are use cases embedded in software. The only, I think, use cases of models that don't get embedded in software and used over and over again are one-time analyses. So an optimization use case would be a greenfield analysis of, I need to find the optimal location to place a new production facility. Or with a machine learning model, sometimes you build a model just to understand what is the relationship between all of my feature variables and what I'm trying to predict. And once I understand that a little bit better, maybe the accuracy isn't good enough to post and give predictions 24/7, but that was useful by itself. And it used to be that your data scientist, statistician, your industrial engineer would build and validate a model in languages like Python, R, MATLAB, Wolfram Alpha, maybe Julia, because those are better suited towards data analysis and statistics. Then they would create some documentation for the final version of their model that they spent months working on, and then throw it over the wall to a software development team, which is probably using languages like JavaScript, C++, Rust, Go, Java, and don't have access to all of the same mathematical and statistics libraries that the statistician had. And they're probably going to be running it on different hardware than the data scientists had too. They might have needed a bunch of cloud resources or GPUs or a lot of memory to do what they were doing. Maybe in production, it's running on a browser or a phone. So even if they had the mathematical knowledge to replicate that work, it's still sometimes programmatically very, very difficult to impossible. So MLOps is the emerging field trying to fix that. So why is this such a hard problem? There's been 2 studies from McKinsey and Gartner Research recently. The McKinsey study stated that 85% of machine learning models never make it into production. The Gartner study from 2022 said 50% of models never make it out of the prototype phase. Some of that is because not all models work in trying to predict the future. Sometimes the data you have isn't good enough to predict whatever you're trying to predict. But a lot of it is, a lot of projects hit a roadblock when you try to integrate them into a dashboard or into an application or into a factory floor manufacturing process. There's a lot of problems there. And the reason why that is MLOps is going to have all the same complexities and challenges of building software, plus problems about monitoring the model accuracy over time, and deciding when a new version of the model needs to be retrained, replacing the old version, and tracking the versions of data that are used to train each of those model versions, and then tracking code used to pre-process the data for every one of those models. So this diagram on the bottom left is from a paper that Google presented at IRIX in 2015. This was the first major industry presentation about how hard this process is. It's called Hidden Technical Debt in Machine Learning Systems. That technical debt is a software engineering term. It refers to when you make conscious decisions to do stuff the easy way. You know there's a clear, better way to do things. And that could mean you implement something that's not as scalable, not as reliable, so it fails more, or maybe it's harder to maintain. And it's called debt because the longer you go without reworking it, doing it the better way, the longer you go without addressing the problem, the more time it's going to take to fix it. And now a lot of people are saying after this paper that machine learning is the credit card for technical debt. It becomes so hard to integrate these systems or software systems that you end up just piecing stuff together in a way that doesn't fit. I like this diagram because it illustrates how little machine learning code is compared to the rest of what is needed to implement it. For example, when I start a new project, 90% of the code I write never gets run in an application, never gets read by anybody else. A lot of it is code for exploratory analysis, statistics, feature engineering, creating visualizations, and some of that gets saved. The part that's needed for traceability, so people can reproduce my results, is definitely going to get cleaned up and documented well. But a lot of it just gets lost in GitHub or OneDrive, sit there forever. And then once a model goes into production and it's being used by people, it can be often less than 5 to 10 lines of code that we'll see in a little bit. You could define a function, read in a model, make predictions on your data, return the result. And that could be it. It could be the most important 5 lines of code in your entire application, predicting something that's like your recommendation engine or forecast for your business. But it could be months and months of work for relatively little proportional work to be taken. Everyone following so far? Does anybody have any questions? So there's 4 main ways that you can deploy a machine learning model, get it into the hands of people that need the results. When I say deploy or send to production, all that means is completing the phase of the product or your project where your model is first integrated into a software system and people are getting the results. Production here is a software engineering term. You usually have a couple environments where you're hosting your software. Development, which is often broken because people are making changes. Stage is the environment where power users are testing it out, finding bugs. And production or prod is where end users are using the software. By that point, there better not be any problems or bugs. So the most popular deployment type are called real-time deployments. This refers to your model running behind HTTP endpoint, which is basically a very, very small backend application that runs one function, invoke the model and return the results. This has been popularized by improvements to Python and R packages that help make them more full stack development languages to build that endpoint to access them with an HTTP request. So with our Titanic model that we saved over here, this model.pickle file, I have this other file, servemodel.py. And in here, we're going to create an application. And this application is going to run one function. It's going to take the data from this request object. It's going to be passed in in our HTTP request that we'll do through the browser. We're going to load in that model file that we saved. And we're going to run model.predict probabilities to get the probability that someone of a certain gender or a certain age will survive the Titanic. So we can run this and show how someone would hit it. So now I'm running this application in Python on my computer. And I can say, go to that HTTP server /predict as we define in the application. And we can say age equals 4 and sex equals male. And get a prediction back. If we change any of these input parameters, let's say 44, now that person's probability of surviving just went down. We would go back and say 5, change it to female. Model seems to be working as expected. So now anyone that has a connection to the internet could hit this server, hit that endpoint, pass in some data, and get some predictions back. So this is for the Titanic. Hopefully, like I said before, there's not another Titanic, but whatever your model is, you can host it in this way. Usually on the cloud, usually you'll set up some authentication, so only certain people can get access to it. But now you can make your model generally available to any software, whether it's a desktop application, mobile application, Tableau dashboard. So when would you want to do this? This is probably anyone's default way to deploy a machine learning algorithm. When you do it this way, you need to make sure that the model results can be generated quickly because there's going to be timeouts over the internet. If it takes more than 60 seconds, this is not a great option. And it's really good if your users expect results right away to show up. And then the only caveat with this is wherever those predictions need to go, that device needs to have access to you. The next most popular deployment type is a batch deployment. In a batch deployment, this is referring to predictions being made in bulk. So in that example, all of your predictions will be generated one by one as new requests come in. If we were boarding a new ship to the Titanic and we could wait until we had all the people going to be on the ship, just make all of those predictions all at once in a big batch. And that becomes a lot cheaper than hosting that API service 24/7, waiting for people to get requests for predictions. So this is usually the most easy thing to implement. There's a lot of cloud tools available that just say, run this script on a schedule. Your other options would be have some sort of front-end application where you can click a button, say, now I have a button that starts my batch machine learning predictions. That can be a little bit complicated. Next deployment type is streaming. So streaming here, I think, is a misnomer because streaming gives the connotation of I'm processing data continuously 24/7. And that's true, but sometimes this architecture, like using this technology for deployment, is really good at doing the exact opposite thing. A lot of people use this for deployments that have very intermittent demand for predictions. So you'll see huge spikes of predictions, and then it shut down and not make any for a long time. And the main technology that enables this streaming type deployment is called a pub/sub, a publisher subscriber technology. It's basically a queuing system. It's a software technology that manages a queue of messages. You have a publisher, it's pushing messages to the queue, and a subscriber that pulls messages off the queue. And then it usually works in a FIFO, first in, first out manner. For machine learning and optimization models, the machine learning model is usually the subscriber. So whoever needs a machine learning request or an optimization model request publishes a message to the queue. The model picks it up, runs the result, and saves it either to the database or pushes it back to another queue for someone else to grab and use in an application. When would you want to use this streaming or pub sub type of thing? Really, any case that works for real time also works for streaming. The one benefit of doing it this way is that, let's say you have a model result and a model that takes a long time to run or a long time to do predictions. Some optimization models are going to be this way. Maybe you want people to have access to send data and get results back whenever they want, but it could take minutes or hours. You could do this to process that result right away and send it back asynchronously, where if you did it in a real-time way, you would hit internet timeouts that would cut off that request. Last deployment type is an edge deployment. This is when your model runs directly on the device that's getting in the input data. So some popular examples of this would be a camera that has some GPUs attached to it that's doing computer vision and image recognition. You might have a manufacturing device that's getting some sensor data and making some decisions about the manufacturing process, or a self-driving car. All of that compute is happening right on that car. And this type of deployment is by far the most difficult. The only reasons when you would want to do this is when your internet connectivity is not reliable. So you couldn't host an API in the cloud and have someone hit that endpoint and get results for their Titanic passage because they don't have internet. At Cargill, we get a lot of use cases where they want to do this machine learning model to collect some data about a farm and get some predictions. But there's not always internet way out in a rural area in the middle of the farm. And that makes doing that very difficult. The other scenario when you would want to push a machine learning model onto a device is when the latency needs or that response time to get those predictions is so fast that you can't even wait for the response to come from a server or from the cloud and back. For example, even if your self-driving car had internet connection 24/7, you don't want to have to wait a half a second for a request to go to the cloud and back to make decisions about, is there a pedestrian in front of me? Do I need to stop? You want that to happen as quick as possible. System that's connected directly to the brakes. And this also poses two other challenges. First, it's harder to monitor the predictions that are coming off an edge device. If it's not connected to the internet, it's very hard to know what kind of predictions. You have no idea if the model is working as you expected it to when you developed it. And second, you can't update it when you need to. If you could figure out that it wasn't working, or you just developed a better model, you need to have some sort of internet connection, wired or wireless, to change the software on that device.
Yeah. Something, is there consideration on, for example, power usage, and that would lead to money for using edge versus the first one? I don't remember. You'll have to bear the brunt of all the calculations of your learning.
Yes, definitely. Especially if you're hosting in the cloud and you scale up to do tons of predictions, it can get really expensive. And most clouds, AWS, Azure, have tools for once you get to that point, you might refactor and do things. Either they have serverless technologies that let you just pay for the compute you use. You can minimize the amount of unused time. I don't know if that answers the question, but the short answer is yes, you could get to a point where your costs are so much in the cloud that you would push it to this.
Yeah, I don't know if that's really happening in reality or not.
I don't know either. Cloud gives so many benefits in terms of the ease of use to build things that you kind of get locked into that ecosystem once you start doing it. And once you do things for a certain way for so long, develop those expertise, then it's hard to kind of refactor everything to be able to run on a device. Yeah, good question. Any other questions before we move on to the next?
So does a place like Cargill, do you host your own applications or do you use like Amazon Web Services?
We do everything on AWS. We have a couple use cases where we push things to run in a plant location, but I think that's the minority, maybe 5 to 10%. Our default is deploy things to the cloud. Now, what happens after you deploy your model? The next thing you have to do is monitor it, make sure it's working. The two types of monitoring that need to happen. The first is regular software logging and monitoring that all code should have. The added complexity with machine learning is monitoring the model. Might have noticed in all of those diagrams, someone is saving the results to a database. And this is very important and often gets overlooked when you deploy your first model. So that enables you to see what's happening with the predictions over time and ensure that they follow whatever distribution you expect for those predictions, that they match whatever was in your training data. And if you can, you also want to monitor the accuracy of the model. And that seems like kind of an obvious thing to say, you want to know how accurate it is. But in some cases, you can't. You can't get the data of what actually happened for your prediction. Some examples of that would be, let's say you have a recommendation. You're predicting, will this person like this news article? And you recommend it to them in an app, and they click on it, skim it, and close it. You have no idea, did they like that article or not? Was your recommendation a good recommendation? You can use some proxy metrics for that, like how long they spent on the article, but you'll never know if they clicked on it because they hated it, they wanted to read it, or they clicked on it because they loved it and just didn't have time. Another use case where it's very hard to know if your model is working or not. Sometimes the act of making a prediction is going to change what would have happened. So if you do predictive maintenance is a very common use case in manufacturing plants where you take a bunch of sensor data out of your factory equipment and predict like if it's going to fail or if some event's going to happen, it's going to shut down your production. And you might predict that some sort of failure is going to happen. They shut down production, change the settings of the machine, maybe do some maintenance. And that changes if it was going to fail or not. Now you don't know, would it have actually failed? Or am I just producing a bunch of false positives, shutting down production for no reason? So monitoring your predictions and monitoring what's called the ground truth, what actually happened. The last thing you want to monitor is the input. New features that are coming in to make those predictions. So you do that because you want to make sure that the distributions of those variables haven't changed. Because if that distribution changes, your model learned the relationship between that old distribution and your target variable. And that changes, now you have to train a new model. And you collect it because data is cheap and you can train a better model with more data. So the word for that, the word for when that data changes is called data drift. So we have one input feature, we'll call it X. We're using that to predict Y. We want to monitor the distribution of all of those input variables over time to make sure they still match what we had in our training data. We want to make sure that the mean stays the same, standard deviation doesn't change, and make sure there's not a lot of outliers or anomalies that come. Because if the distribution, let's say the Titanic example again, the distribution of males and females are different, then we're going to want to retrain a new model based off of that new data. So that's one thing you want to monitor for is data drift. The other thing is called concept drift. This is when the distribution of your independent variable stays the same, but its relationship to whatever you're trying to predict changes. So for our Titanic example again, let's say in the 1940s, 30s, I don't know when the Titanic sank, 20s, 1914, thank you, I appreciate it. Maybe a child was considered like 12 or 14 years old then. But now, on the new Titanic, a child is considered 18 years old. The distribution of ages of our passengers on the boat hasn't changed, but the probability of a certain segment of that population surviving would have gone up kind of significantly. So that's called concept drift or model drift. And if you identify either of those things, you're going to want to retrain your model and push a new version so that people are using the most updated version. So either that happens, or sometimes your project just never finishes. You make algorithmic improvements that help you make a model that's more accurate, or maybe you've just collected so much data over a certain period of time. The more data you have to train a machine learning model, the more accurate it's going to be. And when you have a better model, you're going to want to update whatever one is existing. So how do we go about doing that? How do we update the existing models that we have? There's three main things you can do. You can do it on a scheduler automatically every day, every week, every month. We're going to take all of the new data we've collected, retrain a new model, just click the redeploy button for our software deployment pipeline. You can also do it only when you have identified drift. So you can have some data coming in, you have some alerts and monitoring set up on that data. If drift, either data drift, concept drift gets identified, kick off your machine learning model training script. And in some cases, only for those batch type deployments, you can retrain on every invocation. For example, if I have a model that does weekly forecasts for all of my products that I'm selling, and I only create them every Sunday night so that they can be used the next week, it might take an hour to make all those predictions and 6 hours to train all the models. It's happening overnight. It doesn't matter if I retrain every time I make new predictions. There's four things you should consider every time you update a new model. One thing you want to look at is when you're retraining a new version of your model, how different is it actually from the old version? If you trained on 5 years worth of data, and you're retraining a model every single day, is that one extra day's worth of data actually going to make a significant change in how that model is performing or what it's predicting? If it does, then your model is probably not working very effectively. It's probably not identifying the right relationships that exist in the data, probably fitting your model to the norms. Or if you do the retrain only when you've identified drift, then you should for sure have a different model than you had previously, because you've identified different relationships that are in the data. So if you identify drift and you retrain, you end up with a very similar model, then that's also a problem. So that also gets to the second point, is you want to have unit tests for your models after you train them. You want to save out a holdout set that you can use to simulate data that would be coming in the real world, figure out what your projected accuracy would be on a set of data that your model has never seen. And you want to create unit tests for all sorts of different scenarios and outliers for what happens if bad data passes into my model, what type of predictions does it create, and then what decisions are going to be made from that downstream. If I make a forecast that's wrong because an outlier of data came in and someone increases our supply chain spend by a bunch of money because my forecast was wrong, how do I prevent that from happening? Then after you've written and implemented some good tests, how do you want those to be interpreted? Do you have them automatically, just if all the tests pass, then a new model gets deployed? Or is it extremely critical? Maybe it's a very regulated industry, finance or healthcare industry, and you need to have some human in that loop responsible for predictions being made by that model. They can be held accountable if something goes wrong. So they have to sign on every new model that gets used. And then finally, you should consider what's being updated. Is it a model artifact, which is that binary model.pkl file that we saved in that example? Or is it the code that imports that artifact, applies it to the data and runs the model? Or maybe you have some pre-processing too. Or is it any combination of the artifact, the code, and the programming environment that you run that package versions that includes? So that's going to bring me to the last point for this talk is, what does someone really mean when they say, I have a model? The machine learning industry hasn't really decided on this yet, and that's apparent because a lot of the major model platforms, some of them are open source, some of them are proprietary, define model differently. MLflow is probably the most popular open source machine learning platform. It was created by Databricks, now open sourced. If you save a model with MLflow, you get a directory, a folder of files. One is that model.pickle file, binary artifact. You get an ML model configuration, just a text file with some metadata in there. And then one of those bottom three files defines your Python requirements, the packages used to build that model. Cloudera is a popular data platform. They have a data science workbench that you can use for machine learning or optimization models. They define a model as the endpoint or that REST API used to give you the predictions. So that not only that code, that function that people use to hit that endpoint over the internet, but everything else that is used to run it. So the container that sits in. Amazon AWS Cloud has a machine learning tool called SageMaker. That environment, a model, is defined as a Docker container that contains all of your Python code that you need to run it, all of the Python packages that you need, plus an artifact binary file. And that file has to be in their storage service called S3. Azure, Microsoft's cloud platform, also has a machine learning offering. They have their own custom model format that you can use, or you can use an MLflow model format, or Triton is another format that's starting to be used for deep models. If you use, has anybody heard of Hugging Face before? Hugging Face is an open source platform for deep learning models. If you download a model from that platform, you will get a binary artifact that you can read into Python. So all of these different places define what a model is slightly differently. And so if you're interested in getting into machine learning, something to watch out. That's all I have prepared. Thanks again for inviting me to come present. I hope you found some of this information useful. Be happy to hear what questions came to your mind during.
So yeah, I want to hear from you. What do you think is the current, like the weak spot, let's say, in this whole machine learning business? Is it the lack of the powering tools or the power the functions, or is it awareness in the industry? About those machine learning tools, or maybe it's the lack of the data, or maybe there's a communication. So what do you think is the most sort of like the missing thing in the whole business?
A lot of times it is the lack of data. So a lot of times we'll get people that have a really good idea to solve a problem. And then we ask them, okay, what data do you have to solve that? And it turns out they have bits and pieces of it scattered around, and not nearly as much data as they thought. Or they want to predict something happening on a daily level, but they only have one piece of data for every year that happens. It's just not great. There is some communication gaps too, and just figuring out what is the art of possible with these type of tools and these algorithms. I think those are the main two challenges.
Yeah, it's really helpful. So maybe, I mean, since you are all students, maybe you can give us some advices like what to do, how can we improve or strengthen the existing, at least undergraduate curriculum for, on that part, machine learning, data science. So do you have any suggestions for us?
That's a good question. I'm not as familiar with the changes made in the curriculum in the past 5 years or so. So I don't know exactly what's being offered. I think Python is a good place to start. If there's any classes that do that. I see the industry kind of converging on that language for doing most of the machine learning, especially the more advanced stuff. And even for optimization problems, I use Python every day to interact with Graudate. So that'd be the first thing.
Thank you.
Any other questions or comments about machine learning?
Yeah, I have a question. So when you were talking about different types of machine learning, you kind of said, okay, you were supervised and supervised. And why do you think that you don't see more applications of reinforcement anywhere?
Great question. So a lot of the problems that reinforcement learning has solved recently is just gameplay and simulations. I like to describe reinforcement learning as you're just training an agent to learn from experience inside of a simulation. And games have been the easiest way to simulate it. There's not a lot of things in the industry where I'm gonna simulate my business and have an agent act around in my business to solve problems. So there just hasn't been I think, a killer use case in an industrial problem for reinforcement learning. Besides simple video games, or AWS has this tool where you can use reinforcement learning to train a little toy car, and that's really cool. But it's just never been the best tool to solve a problem, even though it probably could be a tool to solve a problem.
Yeah, I was thinking when we were talking about kind of retraining the model, I was thinking about, well, that sounds like reinforcement learning is kind of continuously retraining it in a cheap way.
Yeah.
But yeah, maybe it doesn't, others are better for other reasons.
Some models, especially like the very big deep learning models, you can also kind of checkpoint and then start the training off from the middle, so you don't have to retrain from scratch every time. You see that with a lot of the new large language models that are coming out. People will just take the current model and then train on top of that using their current data without clearing all the coefficients and starting from scratch. But that's only for neural network type models. All the other ones kind of go from scratch. Those don't take necessarily as long to train. That's a good question. I'm excited. I want to do some more reinforcement learning. I'm looking for ways to apply it to a business scenario, but can't find any ways.
So what you guys do often if you don't have enough label data to train the deep learning?
Good question. We see this very often with computer vision problems. A lot of people have a cool use case for, we're going to put a camera here, we're going to identify what's going on, and we're going to send some alerts to someone for some use case. And it's very easy to collect image data just by setting up the camera and pulling it out of the video. It's very hard to collect labeled image data. It's never labeled when you first get it. So the only way to do that is to label it. There's a bunch of tools now. Some are open source. We use AWS's proprietary, it's called Ground Truth. It's basically a user interface where you can set up a group of people, they get an email, they have 1,000, 100, however many images they need to label. And we just kind of all, people on that project will go and take a couple hours a day for a couple days. There's no easy way to get around not having labeled data, especially for computer vision. There are some tools now that they will try to use a previously trained model to label more data for you. They're basically just getting the prediction from that model and adding the predicted label. I think that's a little dangerous in some use cases because then you are just kind of putting that model in an echo chamber. You're taking its predictions and then you're going to retrain with those predictions and telling it it's ground truth, and it will learn what it already learned. Very good question. feel free to reach out in email or on LinkedIn if you have any other questions.
Yeah, it was.
I think pronounced endorsement for. Nice to also from perspective, we don't obviously we don't put out our-
Good, we're like done, we just gotta write. Yeah, oh, yeah. Pretty good, yeah.
Yeah.
Oh, yeah, we ended up putting together.
Why is it?
Oh, it's the day after. Oh, they're doing 12.
Oh, jobs, you know, they're plug in. They were doing it or not, and so they had. Referred to, oh, they're these bitches to classify it. And so right now,
Yeah.
wages are getting a total.
Who was my, that's not she worked in healthcare AI, but she was my senior in grad school, so she did PDs for PDs or the dynamic systems for her PhD. And she did postdoc here in the IMA, and then she switched to industry.
Make a model or refactor problem statement.
Yeah, we ended up making a model, we didn't